Alright, accelerated chemistry students, this is Mr. Spurk, and this is your chapter 18, section 3 notes on reversible reactions and equilibrium. A reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur at the same time. So if we look at these two equations, the top one we have SO2 plus O2 yields SO3, and then the reverse reaction is SO3 to O2 plus SO2. So we can actually just combine the two into one by using this double-sided arrow, and that shows that this is a reversible reaction. When the rates of the forward and reverse reaction are equal, the reaction has reached a state of balance called chemical equilibrium. Notice in these graphs that after a certain time, the concentrations remain constant. At chemical equilibrium, both the forward and reverse reactions continue, but because their rates are equal, no net change occurs in the concentrations of the reaction components. So what that means is once they reach equilibrium, the reaction does not stop. They keep happening, but they're happening at the same rate. So there are conditions that affect the equilibrium. So although the rates of the forward and reverse reactions are equal at equilibrium, the concentrations of the components usually are not. The relative concentrations of the reactants and products at equilibrium mark the equilibrium position of a reaction. The equilibrium position tells you whether the forward or reverse reaction is more likely to happen. One set of components is often so favored at equilibrium that the other set cannot be detected. When no reactants can be detected, you can say that the reaction has gone to completion, or is irreversible. When no products can be detected, you can say that no reaction has taken place. So now we want to talk about Le Chatelier's principle. The French chemist Henri Le Chatelier proposed what has come to be known as the Le Chatelier's principle. Its principle states if a stress is applied to a system in dynamic equilibrium, the system changes in a way that relieves the stress. Stresses that upset the equilibrium of a chemical system include changes in the concentration of reactants or products, changes in the temperature, and changes in pressure. So concentration, pressure, and temperature are three factors that will affect the equilibrium position. So changing the amount or the concentration of any reactant or product in a system at equilibrium disturbs the equilibrium. The system will adjust to minimize the effects of the change. So if we look at this chemical reaction, carbonic acid yields CO2 plus H2O. If we add CO2, the rate of the reverse reaction increases. So think about it. We are adding more product. So to alleviate that stress, this reaction is going to produce more reactants. If we remove CO2, so if we were to remove CO2, the reaction would move in the forward position. Carbonic acid would decompose faster to make up for the lost CO2. Increasing the temperature causes the equilibrium position of a reaction to shift in the direction that absorbs heat. In other words, it will shift in the direction that reduces the stress. So if we were to heat this reaction, so add more heat, it would push the equilibrium to the left. Because heat is a product, so heat is here. Sorry, I can't keep clicking things. If we add more heat, it's going to alleviate that stress by moving towards the products. If we remove heat or cool the reaction, it's going to move towards the right. It's going to try to make up for that lost heat. Equilibrium systems in which some reactants and products are gases can be affected by a change in pressure. This pressure only affects when the reactants and the products are in the gaseous state. A shift will occur only if there is an unequal number of moles of gas on each side of the equation. So for gaseous systems, when we're looking at pressure, we are focusing on the moles. So if you look, we have 1 mole of N2, we have 3 moles of H2 on our reactant side, so a total of 4 moles, and we have 2 moles of ammonia gas on the right. So if we add pressure, if we increase the pressure, it's going to shift towards the side with less moles. So we're going to shift towards the products. If we decrease the pressure, it's going to shift from the right-hand side to the left side to allow more space or more moles of gas to be produced. Catalysts decrease the time it takes to establish equilibrium. However, they do not affect the amounts of reactants and products present at equilibrium. Chemists express the equilibrium position as a numerical value. This value relates the amounts of reactants to products at equilibrium. So in this general reaction above, the coefficients A, B, C, and D represent the number of moles. The equilibrium constant, or KEQ, is the ratio of product concentrations to the reactant concentrations at equilibrium. From the general equation, each concentration is raised to a power equal to the number of moles of that substance in the balanced chemical equation. So if we look back at that chemical equation, lowercase a is the number of moles for A. We can see that the concentration of A is raised to that lowercase a, so the number of moles. And you can see that this is the products divided by the reactants. The value of KQ depends on the temperature of the reaction. The size of the equilibrium constant indicates whether the reactants or products are more common at equilibrium. When KEQ has a large value, such as 3.1 times 10 to the negative 11th, the reaction mixture at equilibrium will consist mainly of product. When KEQ has a small value, such as 3.1 times 10 to the negative 11, the mixture at equilibrium will consist mainly of reactant. When KEQ has an intermediate value, such as 0.15 or even 50, the mixture will have significant amounts of both reactant and product. So let's express and calculate KEQ. The colorless gas dinitrogen tetroxide and the brown gas nitrogen dioxide exist in equilibrium with each other. That equation is N2O4 yields 2NO2. So if we have a liter of the gas mixture at equilibrium contains 0.0045 moles of N2O4 and 0.030 moles of NO2 at 10 degrees Celsius. Write the expression for the equilibrium constant and calculate the value for the constant for the reaction. So remember that KEQ is equal to the concentration of the products raised to their coefficient divided by the concentration of the reactants raised to the power of their moles. So KEQ is equal to, our product is NO2, and we have 0.03 moles. And remember that this is concentration, so we need to make sure that we divide by that 1 liter. It says that we have a liter. And other times it will not just be 1 liter, so we have to make sure that we're always thinking about that. It needs to be in concentration. And NO2 has a coefficient of 2, so we are going to raise this to a power of 2. And now we're going to divide by our reactants. And our reactant has a concentration of 0.0045 mole per 1 liter. The units are going to cancel out. And when we multiply this through, we are going to be left with 0.20. So our KEQ value is 0.20. 1 mole of colorless hydrogen. Let's do another equation where we find the equilibrium constant. This one is going to be a little bit trickier since we're given some different information. So make sure you put your math hat back on and take good notes and pay attention. This does get a little tricky. So 1 mole of colorless hydrogen gas So we have 1 mole of hydrogen and 1 mole of iodine vapor are sealed in a 1 liter flask, and they're allowed to react at 450 degrees Celsius. At equilibrium, 1.56 moles of hydrogen iodide are present. Together with some of the reactant gases, calculate the KEQ for the reaction. So what we know is that the initial concentration, and that's an I for initial, of H2 is 1 mole per liter. The initial concentration of I2 is also 1 mole per liter. And we know that the equilibrium concentration is equal, for HI, is equal to 1.56 mole per liter. And they're asking us to solve for KEQ. So what we need to do first is find out how much H2 and I2 are consumed. So remember, our equation is H2 plus I2 yields HI, 2HI. So basically, what this means is X plus X, because these are unknown concentrations at equilibrium, yield 1.56 moles. Sorry, that's just moles. So we know that this is at equilibrium because we're trying to figure out how much is consumed. So let's write at equilibrium. So we can solve this equation. So 2x equals 1.56 moles. So x equals 0.780 moles. So that means that 0.780 moles of H2 and I2 were consumed during this reaction, because that is how much was needed to form 1.56 moles of HI. So our next step is to calculate how much H2 and I2 remain in the flask at equilibrium. So we know from our initial conditions that initially we had 1.00 moles of H2 and I2 initially at the beginning of the reaction. And we know that we consumed 0.780 moles of each. So that means that at equilibrium, we have 0.22 moles of H2 and I2. And this is at equilibrium. So again, this is our initial values for H2 and I2. This is how much was consumed. And this is how much is left over at equilibrium. So now we can solve for KEQ. So we know that KEQ is equal to the concentration of the products. And remember, it was H2 plus I2 yields 2HI. So we need to square the concentration of HI divided by H2 times I2. And we know that we are in a 1 liter flask, so we can just divide our mole values by 1 liter. So we have 1.56 molar, or moles per liter, remember, squared, divided by 0.22 molar times 0.22 molar. When we multiply and divide this through, we are left with a KEQ value of 50. So remember, a KEQ value of 50 means that we have some products and some reactants. We're not really one one isn't really favored over another. All right, so we got through that one. In review, at chemical equilibrium, both the forward and reverse reactions continue, but because their rates are equal, no net change occurs in the concentrations of the reactant components. Stresses that upset the equilibrium of a chemical system include changes in concentration of reactants or products, changes in temperature, and changes in pressure. The size of the equilibrium constant indicates whether reactants or products are more common at equilibrium. And remember that our KEQ expression is the concentration of the products divided by the concentration of the reactants. All right, we did it. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.